So today it's all on you guys. I've got all the homeworks loaded up here in the PowerPoints, and so we can go through your questions. We could do Kahoots, we could do whatever you want. Yeah. If we do the Kahoots, I might get the pump primed and get some questions going. There was some that we hadn't done. Go ahead. Oh, the reduced variables? Yeah, so that's yeah. This one down here, number no 6. Yeah, here we go. Reduced pressure. Yeah, very good. So we have to look those since it's homework, you have to look those numbers up offline, I guess. But um so we need, can somebody look up quickly the critical temperature for water? I think it's 647. Yeah, so TC 647 Kelvin. And so SATP, that, so this is the ambient temperature, so that would be room temperature. SATP, so that's 298 Kelvin. So you just take the ratio of those. So TR is equal to T over TC. Okay, and that's 0.461. We've got the answer right here. So it would have the same pressure that at this reduced temperature at 0.461, it would behave like some other gas that had the same reduced temperature at 0.461. So like if we knew, can you look up CO2's critical temperature? 304? That's good enough. So 304 Kelvin for CO2. So if we have TR is 0.461, and that's equal to T over 304 Kelvin, then the temperature that CO2 and water would act similar would be 46% of 304. So 140 roughly. CO2 at 140 Kelvin would behave like water temperature, 298. So that's why we use those reduced temperatures and pressures. When I say behave like, it would have the same equation of state, essentially, the same pressure, temperature, volume. So at it, assuming ideal pressure for CO2 at 140, and say using the van der Waals equation for CO2 at 140, you'd have the same error there as you would have for water at ideal and real conditions at 298. So that's a way to think of it. And that comes to that from that Z, the compression factor. So this is 1, so Z is equal to PV over nRT, which for an ideal gas would be 1, but for a non-ideal gas, there'll be regions where attractions dominate and regions where repulsions dominate. So here you could think of fixing the volume, fixing the temperature, fixing the moles of gas, and measuring the pressure. And so here the pressure is lower than you expect, and here the pressure is higher than you expect. And so this would be attractions dominating, and this would be repulsions dominating. And this axis is say we could say temperature. What about the Clausius-Clapeyron equation? Are you all good with that one? You did that in the lab. Remember, you used the vapor pressure and then you used the Clausius-Clapeyron equation to calculate the enthalpy of vaporization for your gases that you used for the van der Waals equation. And I guess y'all have turned those in already. Yeah. So what were your results? I mean, how did the delta H of vaporizations compare to the literature values? No, they weren't. They shouldn't have been. So if y'all like made this case that they were, close and it was a good estimate, no, it's not a good estimate. So the Maxwell construction looks right and it behaves correctly, but it's way off. It gives you even a nice logarithmic dependence on pressure. If you did the pressure plot over 1/T, you got a straight line. That's interesting. I mean, that shows us that in theory it works really well, but all of the delta H values, the slope of that line was way off from the literature value, so it should have been. So that's good. That'll make you a little warm and fuzzy. Okay, so the and I've often wondered if there's maybe a correction, like maybe it's consistently 80% or something like that, where you could say, yeah, this is a good model and it gets you, say 80% consistently. But anyway, what's your next question? Yeah, all the different phase diagrams. That's the major part of the test. So let's go. Mm-hmm. Yeah, for sure. Let's start at the beginning. Here's the PT diagram, pressure temperature. And so first of all, anytime you see these, I mean, think of the axes first. So, we've got a PT phase diagram. So pressure, temperature. So, at low pressure and high temperature, this is all gas. So you want to label your phase diagrams, with their phases first. And so then low temperature, high pressure would be solid. And then in the middle is liquid. And so then these lines are the equilibrium lines. And so this line is sublimation. And the reverse of that is deposition. So like if you have a gas and it's depositing on a surface, it's going from liquid it's from gas to solid. If it's going from solid to gas, it's sublimation. This curve here between liquid and gas, this is, obvious, it's boiling and condensation. And that's also what we would call VLE behavior, vapor liquid equilibrium. That's the VLE line. And it's getting too busy, so I'm just going to draw a line over here, and this is melting and freezing. Let me quiz you on some of these things. This is something that is, it's embarrassing when you miss some of these questions, like um, like ice melting. Ice melting, is that exothermic or endothermic? Ice melting.
Or no.
So ice is the system, and then where's the heat going? Is it coming out when it melts or going in when it melts? Right? We put ice on things to cool them down. Right? So the ice melting is endothermic. So yeah, those are don't most those simple ones on the test. Boiling water, exothermic or endothermic? Boiling water. What's that? Endothermic. You have to put it on the stove, don't you? You're putting heat into the water and you're breaking those hydrogen bonds and turning it into a vapor. So it's endothermic. So you got to get your thinking correctly about the system when you say ice or when you say water, you're talking about the system. So you identify the system and determine where the heat's going. The heat's going into the water to boil it. Just because it's hot to your hand, that's because it's condensing on your hand. And then condensation is exothermic, right? So you got steam, it condenses to water, it gives off its heat, it burns your skin. Okay, so condensation is exothermic. Freezing, exothermic. You're putting it in the freezer and sucking the heat out of it. So the water is giving off its heat. It's exothermic. So water's leaving, heat's leaving the water, and then it's freezing. So freezing is exothermic. Um, and then sublimation. So we worked on the easy ones. What about sublimation? It would be endothermic because it's going from solid to gas, and you're breaking all the associations, the intermolecular attractions. Yeah. And then the opposite deposition would be exothermic. So good. I'm glad we covered that because we talk about these more difficult concepts, I think, and then I'll put a few of those on there just to kind of check people and they'll get them backwards. So that's good. Okay, so those are the going across these lines. That's what we're talking about, these changes. So phase changes here. Oh, it's too far up there, so I'll just stay seated. Um, these phase changes are exo and endothermic when you go across these lines. So when you're going from liquid to gas, you're boiling, and so it's exo going one direction, endo going back. Yeah. Okay. Um, I don't show the critical point on here. Where would it be? Way up here at the top. Yeah. So that would be the critical point. So this would be TC. This up here would be PC. C being critical. And then volume is not shown on this plot, but we would have a volume of VC somewhere. Um, What about number 5 here? Refer to figure 1. The line through letter D has a negative slope. This indicates which substance that we're dealing with, water. And because the liquid is the liquid is more dense than the solid. So if we press on the substance here and it becomes a liquid because the liquid is more dense. It takes up less space. Most other substances, that doesn't happen. I don't know of any others. There might be some exotic substance that happens, but water's the only one I know of. Okay. And again, I made a point that that's why we have life on Earth. Okay. Splitting rocks and making soil and things like that. And also in the marine life and stuff, when the water freezes, it floats. If it froze from the bottom and the whole lake froze, then the fish would die. Okay, so let's go to the PV phase diagram. We look at our axes, PV. Now this is only showing it's missing the solid piece. It's just got the liquid. So let's label everything. Let's start out here at the high volume, low pressure. We don't really have much low pressure, but over here it's at letter C. That's going to be the gas. Okay. We get over here to A, and that's a liquid. And so this region right here is the VLE region, vapor liquid equilibrium. And then this is VC, critical volume. This is PC, the critical pressure. We don't have the critical temperature on here because we don't see the temperature axis, but we do have the isotherm labeled. And so this isotherm goes through this 304.12. That's TC. That's the isotherm that cuts through here. So here at 258, I've got a couple of volumes marked. So 258 Kelvin, I've got this mark here at 0.08 liters per mole, and we're asked what's the density of the gas phase. So we're over here at 0.31 liters per mole. So so let's just do this one. Density, rho, is equal to mass over volume. So the volume is 0.31 liters per mole. We need the mass. So what do? Well, this is CO2, looking at the chart. And so that's 32, is it 44? Yeah, so it's 44 grams per mole. Per moles cancel. We got grams per liter. Hooray. So we should get 0.14. We could also calculate the density of the liquid. So 4. It's grams per milliliter, so we should probably make this milliliters. It's asking for grams per milliliters. So this would be 310 milliliters. Okay, what's the density of the liquid? Well, we still have 44 on top. But we can see from our phase diagram, the liquid is much more dense. So this is the liquid spot, this is the vapor spot. And so 0.08 or 80 milliliters per mole. Moles cancel. It's about half. So 0.55. So since we have volumes on this chart, we can use that to calculate densities. I was nice to you guys. A few years ago, I didn't have this calculation on the homework, but I thought it was obvious, so I put it on the test. Nobody got it. So that's an example of responding to, a situation where like, oh, I thought people would figure this out on the test, but you're on the test, you're stressed, you're like, oh, this is a new problem I've never seen before. And so I went ahead and moved it over to the homework. Yeah, so there's really no way to be like, let's say I look at the pressure. I've got whatever pressure this is. Let's do 40. Okay, let's make it easy. We'll be at 40. So I've got 40 bar in my container, and my container for 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 this temperature, whatever temperature I'm at, is about 0.25 liters per mole. Okay, so I'm right here, but I can't actually be there on the phase diagram. That's what's in my container, but I have two phases. If I'm in this yellow region, I have two phases. And so then I would draw this tie line over to the right and over to the left. And that would be the relative amounts of those two phases. I'm a little bit closer to the gas, and so I had more moles in the gas phase than I have in the liquid phase. And then we would do the lever rule on this one. So coming up with that. Yeah, yeah. So whatever, that's why I draw the little seesaw to balance it out. And so just using your chemical intuition, your physics intuition, you'd have to have a heavier weight on this side than this side to get that to balance. Yeah. We found at a garage sale when my kids were little this little toy for kids, and the numbers, it was a balance, and the numbers were the different sizes of plastic so that they would all balance. So like if you had a 5, it was a big heavy 5, and it weighed the same as a 3 and a 2. So you could put the 3 and the 2 on one side and the 5 on the other side, and it would balance. I thought that was a really cool teaching tool to kind of show the magnitudes of the numbers. Yeah. And addition and things like that. Yeah. So that was really a fun tool. Kids didn't play with it, but I loved it. I was like, so Jennifer's like, "Are we really buying that?" Yes, we're buying this. Okay. Nick.
He is the critical.
Yeah, so here, yeah, D, and I scooted it as far to the left as I could without getting inside the liquid region because I wanted to be under the VC. So VC comes up here like that. And so it's in a smaller container than VC. It's above TC and it's above PC. So that's the supercritical fluid criterion. The criterion would be in a smaller container than VC, so less than VC, but greater than T and greater than P. So it's high pressure, high temperature, and really compressed. Yeah, so we're just cramming it in. It's like supercritical CO2. We start out with it at room temperature where we start just jamming it into a small container, raising the pressure up, and we're about putting a number of moles in. And so we have way more moles than should fit in that container. So it's below its molar volume. Yeah. Okay. So that's the PV phase diagram. We did some other pressure units here. We did torr and inches of mercury. Any issues with those? Just you'll have those conversion factors on your spreadsheet if I mean on your periodic table if you need them. No, you should put the Clausius-Clapeyron equation on there and Antoine equation and those things. Yeah, for sure. But I've got to tell you what units the Antoine equations are, like these units, because like in this case, it's giving you the pressure in torr, the coefficients, and so that's an irritating thing when people use coefficients or constants like that, and they don't use units. I mean, I get furious when you guys don't use units, and I get really furious when you have a resource on the internet or whatever, and they just give you these three numbers, A, B, and C, and assume you know that it's in torr because it could be in bar, it could be in atmospheres, it could be in pascals. Pressure is crazy. It's like 5 units: torr, inches of mercury, atmospheres, bar, pascals. Um, there was another one I was thinking of. Yeah, I did atmospheres. Yeah. Anyway, it's crazy. Okay, and then so now we got describe this system. Okay, first of all, what kind of diagram is it? Don't look at the caption. Yeah, that's right. It's a TX phase diagram. Okay, and it's a partially miscible liquid system. So this is the partially miscible piece is talking about this region right here. Okay, and then what's this right here at C? What is that pinch? Yeah, azeotrope, a low boiler. Just a second. Okay. So here, this is a TX phase diagram. So all of this black line is all boiling point. So the boiling points of every combination, right? So this is a combination here. We'll just say XA. I don't know what we have here, but XA. So this is pure A on the right, pure B on the left. So these are the boiling points for A and B. Oh no, B up here. Sorry, this is XB. That was tricky. Okay, so B is up here on the right, A is on the left. Those are the boiling points of the pure substances. But then every combination of A and B follows this black curve. So this black curve are the boiling points of every combination. And there is a combination right here where the vapor and the liquid composition touch. And that pinch is what we mean by an azeotrope. And it is low, it is the lowest boiling point on the page. So that's why we call it a low boiling azeotrope. It boils lower or below the pure substances. Does that make sense? Even you asked what it was? Yeah. Mhm. Yeah, so that like in the pot, you're saying? Okay, so if we had that azeotrope in here, then the vapor composition, even all the way up to the top of the fractioning column, would be whatever this is. Let's say this is 0.4, right? 0.4. And so this right here would be 0.4B, and the vapor, I'll draw some vapor coming up here. So YB is equal to 0.4, and this is XB. So remember, YB is the vapor composition and XB is the liquid composition, and they're the same when you have an azeotrope. And that's why organic chemists, most of the time, they don't like azeotropes. You're trying to separate compounds with fractional distillation, and you keep getting the azeotrope over. So you can't separate a low boiling azeotrope using fractional distillation. Because, what's that? A is here on this line. So this right here is A. So this would be XB would be 0.4, XA would be 1 minus that, would be 0.6. So 0.6A. Not ever in a collection flask, because you get whatever the low boiling thing is. The lowest boiler comes over on the collection. And so a low boiling azeotrope, whether you start on this side, let's ignore the fact that it's a partially miscible system. Let's take point E through fractional distillation. And so then it would come over here because it would condense in the column and it would drip down and re-evaporate and condense and re-evaporate. And so that fractional distillation does this little zigzag, and these are your theoretical plates until this makes it all the way to the top. It's the most volatile thing. Yeah. And so then if we started on the right, we had too much B, we would collect the azeotrope. If we had too much A, meaning we were on the left side of the azeotrope, so if we're over here and we come up and fractionally distill, it would still bop downhill, and the collection flask would collect C. Yeah, in this case.
What if it's like the it's the regular temperature.
Yeah.
How can you tell which one is more likely to make the pure air pure B? Is it just by like the
Oh, yeah. So if we didn't have an azeotrope, so we just had let's take this same thing. So we'll kind of model it. So this is XB, okay? And so we just had the regular old, and this is actually called a zeotrope. Azeotrope means it's not a zeotrope. Okay. And so I drew that line a little too straight. Let me erase that. So if we have this situation, A has the lower boiling point, so A would be what was collected in the flask.
Oh,
Yeah. So if we started over here and we went up and it would fractionally distill and it'd bebop down, yeah, and A would come off, and that's what an organic chemist loves because now they can separate A from B. Yeah. That's right. Just wanted to listen to it again. Yeah. Yeah. It always goes downhill. Collection flask is always the lowest boiler, right? You have the hottest, you have the mixture in the pot, and then your lowest boiling thing is going to be most volatile. It's going to have the highest vapor pressure, and it's going to come out top. Or it's going to go higher in the column, and then it's going to be condensed, and it's going to collect in the collection flask. Yeah. Okay, if the two phases were mixture A were fractionally distilled, blank would end up in the still bottom. 30B, 30B. And so if we start at A, we fractionally distill, we get this, and then we collect the azeotrope. And what we're doing is we're removing excess A. So if we keep removing excess A, the pot will move uphill. So the boiling point of the pot will change. As we remove A, then I'll have a composition that's right here. And then if I remove some more A, it'll move uphill a little bit more. And if I remove even more A, it'll move uphill. So the pot boiling point will keep moving up until it gets to dirty B. And I always leave the word dirty in there because the pot's a dirty place. Yeah, so it's going to stay all the non-volatile residues down there, and then whatever B you have excess.
so it's
Never clean. It's always dirty. You can't use the pot. Right now, let's say you have a pretty big volume, and we remove that azeotrope. So we've got, and then we start to see. So the azeotrope condenses at this temperature. So we see this temperature at the top of our flask, right? So we're looking at that. As long as azeotrope is condensing on that thermometer, it will stay at the condensation boiling temperature because condensation and boiling are in equilibrium. So whatever the condensation temperature, that's the same as the boiling temperature. So it will stay right there until we run out of A. So this pot will be creeping up, but we'll still be distilling down. Whatever little bit of A is left will make the azeotrope, and that temperature will stay stable on the thermometer. And then all of a sudden, we just don't have any more A. So we can't make the azeotrope. And so then B will be making it up there. So yeah, the pot's dirty, but there's some clean B in the pot too, and that clean B will evaporate at B's boiling point. So this is the boiling point of B. T boil for B. And so we'll look at that thermometer and we'll start to see it move pretty quickly. So when the thermometer starts running away and going to a new temperature, we know we're done with the azeotrope. So we pull that flask off and put another one on and try not to make a mess. We're getting an $80,000, if the grant goes through, an $80,000 distillation unit. And it has an automatic cow on the end. Think of a cow, right? Right? And so it's got hoses that come off of this to our collection flask, and it monitors the temperature by computer. And when the temperature runs, it goes and starts sending the next fraction to a new collection flask. Yeah, it's very cool. Yeah, so the computer system and everything, and you can pull a vacuum on it so that you don't have to heat everything up because heating it up, causes more reactions in the pot. And so if you could do a vacuum distillation, you could get better separation, and you would. And the packing material is a spinning Teflon band, and it's like ejecting the fluid against the walls where it can interact better with the temperature gradient. And anyway, it's crazy, crazy. So we're trying to get our perchloroethylene cleaner than 5 parts per million. So think about that. It's 99.9999. You count it up to 5 nines and a 5, and that's not good enough. So, yeah, so we're trying to get it even cleaner than that. So that'll be exciting. So yeah, once we get to that boiling, or once the A is gone, then the temperature will run towards the boiling point of B. Um, and the pot will still be higher than that because the dirty stuff, so that it'll have a boiling point elevation because it'll have some extra trash in it. But the condensation temperature will be the boiling point of pure B. And then you can collect that for a while. And so you can purify some B, but the pot's just going to get dirtier and dirtier, more and more concentrated in trash. And so you don't ever want to boil it dry. And so you look down when you have a few hundred mils left, you stop the distillation, and then you have still bottoms. And the still bottoms are actually a hazard class that you label the waste as a still bottom, and that's its own waste category. Yeah.
So and also the pure vapor pressure.
This is the pure, not the pure vapor pressure, but this is the boiling point of pure B. Yeah. And this over here on the A side would be the boiling point of pure A. Here I labeled this while you're looking down. Reagan. This one here is the boiling point of pure A. Okay. Now in this case we have partially miscible systems, and so if we cool the condensate down below this temperature, this is TUC, upper consulate temperature. If we go below that, we can have phase separation in the liquid phases. So that's when we have 2 layers in our flask. We don't have to though. If we're on the outside of that line, like at E, it's homogeneous. Even though we're below the upper consulate temperature, we just have one phase because it doesn't have enough A for phase separation. But when we're over in this region, it has enough A to form an A-rich phase, and it has enough B to form a B-rich phase. But these curves here tell you how concentrated they are in A and B. So this is on the right side, since that's B, XB, this is the B-rich phase, or layer, I can call that. And this line on this side is the A-rich. It looks like pitch. And we don't know, without knowing what the substance is, which is more dense than the other, but one will be more dense than the other, and so they'll have an upper layer and a lower layer, but we can't label it upper and lower without knowing which is more dense.
Ralph Lauren.
Yeah, it's coming up. In this one? Yeah. So in this diagram, the dashed lines are which law? Routes? Everybody agree on routes? Okay. Routes laws, yes. And so they go straight from 0 on either side to the vapor pressure. So P, typically these are labeled P star. And so in this case, this is carbon disulfide and acetone. So this is P star for acetone. And over here is P star for CS2, carbon disulfide. And so those lines that connect the pure vapor pressure to zero, that's Raoult's law. Because it's P is equal to X A P star A, right? So it goes, X goes from 0 to 1, right? The mole fraction, 0 to 1. And so it's just a 0 to 1 times the pure vapor pressure. When it's a pure substance, you have an X of 1, so it's the pure vapor pressure. And then if it's 50-50, you get half of the pure vapor pressure. When it's 10%, you've got 10% of the pure vapor pressure. So that's Raoult's law. And it applies to, I'll just use my phrase, it applies to dirty solvents. So if this is carbon disulfide, and over here this is pure carbon disulfide right there at 1, when it's 0.9 or 0.95, it's dirty carbon disulfide. And so Raoult's law, you see the green line, or the solid line and the dashed line merge right there. And that's telling you that Raoult's law applies. Yeah. And then for the acetone over here, it applies even longer here. So this might even apply down to, 90% acetone. So those are the places where Raoult's law applies for the real data, like it gives accurate vapor pressures for the dirty solvents. Notice that I can't say which is the solvent because it depends on which end of the diagram you're on. If you're on if whichever one you're close to the number 1. So we're close to 1 on the carbon disulfide here. So that's dirty carbon disulfide. Dirty CS2. And then if we're over here, we've got mostly acetone, so that's dirty acetone. Henry's law just replaces the mole fraction with a constant, the Henry's law constant. So if we just extrapolate this line, it's a linear extrapolation, extrapolate this line all the way to the other side, then when it hits this other side, we have the Henry's law constant. I think, are they labeled K in this case? KH? KH times the mole fraction times KH, right? X A times KH is equal to the P for A. Yeah, so I said earlier I made a mistake. I said we replace XA with KA, but we don't. We replace the pure vapor pressure with KH. Yeah. So we still keep the XA. That's our 0 to 1 scale. And when it's 1, we're multiplying by the Henry's law constant. Now that's never accurate over on the 1 side. It's only accurate down here on the solute side. So dilute. So this is dilute CS2. See, we're close to 0 CS2. And over here, we're close to 0 acetone. So this would be dilute acetone. And so Henry's law constant applies to those dilute situations. Say it a little louder. Yeah, right here, 100% acetone, P star, yeah. Yeah, so dilute acetone, so then the Henry's law line for acetone would be going up at this slope here. It would have this slope like this. Yeah, and it would come all the way over to the left side and be like out the roof of the building. It'd be so high on the left side. So wherever this really steep line comes all the way across and where it hits this line, that's KH for acetone. Yes. Yeah. because what we're doing is we're trying to find out what's that maximum value hit the opposite axis if we extrapolated it across. And so some of these Henry's law constants can be like 500,000, you know, or something enormous. Yeah, you have to look them up, and it's the frustrating thing about Henry's law constants is that they are like you have a different set of constants for every blend. So there's a Henry's law constant for acetone in carbon disulfide. It has nothing to do really with acetone and anything else. So for acetone in water, another Henry's law constant. Acetone and yeah, so it's just experimental data that you measure and you extrapolate and report the constant. Yeah. Oh, you'd have to have it. Yeah, yeah. And I mean, the only way I could maybe have you calculate it would be if you had two data points. So you had, I mean, obviously 0 is the data point. And if I gave you like, this is dilute acetone. So if I said 0.05 mole ratio of acetone had a vapor pressure of 50 torr, what's the Henry's law constant? So you've got the slope, and then you just extrapolate it all the way to the other side. So let's do that real quick. It sounds like a fun calculation. Say that again. Yeah. No, it's where it hits the opposite side. So this is a really dramatic. These are really not ideal solutions, and so the Henry's law constants are not even on the screen. Yeah. So if I said so X acetone is equal at 0.05 and P acetone was 50 torr. Okay, so rise over run, right? The slope is equal to 50 torr divided by 0.05. Okay, so the fives cancel. So that's a 1, that's a 1. So that's 10 divided by 0.1, or that's 1,000, right? Did I do the math correct? I started with 10, I divided by 0.01, so I moved the decimal place 2 more places. So 1,000 torr. So if we extrapolate that all the way across a unit of 1, we get 1 unit of that slope. So my Henry's law constant would be 1,000 torr. So that's where it would hit the opposite side. This thing, if I measured one data point here at 0.05 and I measured the slope, rise over run, and my run was only 0.05, if I extrapolate that over, I get 2 more decimal places on that number and it goes up to 1,000. So that's where it would hit, and that would be the Henry's law constant. So then if we needed the pressure of acetone at say at 0.1, I'll say, I'm trying to figure out my terms here, at X acetone equals 0.1. So 10% acetone, then we would use that Henry's law. We would say P acetone is equal to 0.1 times 1,000 torr. That's how you would use the Henry's law constant. So this is equal to KH. And so it'd be 100 torr. And that looks about right. Like, I mean, even though it's just like if we had 0.05 and we went another unit over, it would be around 100. That's Henry's law and Ralph's law. Well, that we would, no, really, but that was that Margulies equation and all of those things. I was just really showing you how you get these middle pieces. Yeah. So, yeah. The solid, we don't have any solid phase diagrams on there. We all okay with those? I mean, the melting points and you know what I'm talking about? I mean, let's say, look at that video. Look at the solid ones again too, because solid melting points and stuff, incongruent melting and all of that, that's all on there too. So